Thank you very much to the organisers QCware for hosting this event, and thank you to all the sponsors that have made this possible. It's a real pleasure to be back here again, so thank you very much. So my name is Simon Phillips, and I'm the Chief Technology Officer, CTO at OQC, Oxford Quantum Circuits. My role within OQC is to take our company's high-level vision and mission, which is putting quantum in the hands of humanity and turning that into a strategy and a technical strategy that we can execute against. So it's a real privilege to be someone that can help shape the way we build quantum computers, the way we use quantum computers, and what the future of quantum looks like. That's only really made possible by the amazing team that we have at OQC. We have over 120 people based in the UK and here in Japan. So at OQC, we build quantum computers. We build superconducting quantum computers based on our core technology, which is a novel implementation of a transmon qubit called the coaxmon. Now, the coaxmon is our core patented technology that enables us to solve some of the major challenges with superconducting circuits as we build quantum computers. And we've just recently launched our third generation of quantum computer called Toshiko. And we've launched that around the world, including Toshiko right here in Japan, in Tokyo, in a data center, which we'll talk more about in a moment. Japan is incredibly important to OQC. We set up our office in Tokyo 2 years ago, and we've been met with a lot of enthusiasm for quantum computing. And we can see here these last 2 days that there's a huge amount of support for quantum computing and a huge drive for quantum computing. We've been incredibly privileged that our last two funding rounds, our Series A and Series B, were led by Japanese VCs, University Tokyo Edge Capital and SBI respectively, and we see a long future for OQC in Japan. I'd also like to introduce our Japanese country manager at Sushi Segura. Segura-san has over 30 years of experience in both high-performance compute and IT infrastructure in Japan and internationally as well, and he'd be happy to kind of take any questions on OQC going forward, so please do reach out to Segura-san. So I'm going to kind of give you a bit of a brief overview of OQC if you haven't heard of us, and some of the fun tales and stories that have led us to be here today, and some of the things that we see are going to be important going forward into the future. So as I said, we spun out of the University of Oxford in 2017, so not that long ago, based around this core implementation of a new transmon qubit. So we know transmon qubits have been around the longest. They're the most evidenced, they're the most engineered, they're the most flexible type of qubit that we know today. And when we spun out, we had a new implementation. It's called the coaxmon. It's a coaxial transmon. And what that means is we take all of our microwave wiring out of plane, like a traditional transmon, and put that into 3D. So we have control wires coming in at the top, readout wires at the bottom, and we have some really neat two-sided fabrication. That means our qubits are a really tidy unit cell that have very low crosstalk. So some of the lowest crosstalk reported on any superconducting circuit. That enables us to scale our full systems with less challenges. There's always lots of challenges in building quantum computers, but less challenges than some of our other superconducting counterparts. That enabled us to very quickly build our first full-stack quantum computer. Now, building full-stack quantum computers is incredibly difficult. We've built processors, but we have to build signal chains. We have to implement cryogenics. We have to enable ways for people to access quantum computers. So in 2018, we built Sophia. Sophia was a 4-qubit quantum computer and became one of the first accessible machines in Europe. In fact, we did an experiment with what is now Quantinuum, Cambridge Quantum, back in the day. We did a short hop across our office internet to run an algorithm on Sophia back in 2021. Fast forward just a short space of time, we then built Lucy. Lucy was our full-stack 8-qubit machine, and because of the coaxmon, we were able to move from 4 qubits to 8 qubits relatively quickly, and Lucy became the first European quantum computer available via AWS Bracket. Now, what that meant for OQC was a real discipline in engineering. We found very quickly, we ran Lucy for over 2 years on AWS Bracket, and what that taught us as a company was we've now got a green light on a dashboard on AWS, and we need to keep that green 24 hours a day, 7 days a week for 2 years. And this is using cryogenics. A lot of people think cryogenics are clunky and unstable, but we managed to keep that system live 24 hours a day, 7 days a week for over 2 years. And it's a real testament to the engineering discipline that we built within OQC. Fast forward a little bit of timeline here, and now we're building Toshiko. Toshiko is our latest 32-qubit machine. Toshiko has been designed specifically and uniquely to be installed into co-located data centers. And there's a couple of reasons why we ended up building our machines in co-located data centers, including the machine that's installed in Equinix's IBX TY11 data center just down in Adiaki near here. So what actually happened there was when we were building Lucy and we're getting ready to go live and we're running all of our tests, in the UK we had a power cut. This happens quite a lot. We see it everywhere. The power went off in our lab. It's very unfortunate. And what that meant was a piece of equipment, a small piece of equipment just didn't restart. We didn't spot it. The machine warmed up. We lost a processor. It cost us 6 weeks of development time launching Lucy because of one power cut. So doing what all good engineers do, we started designing batteries and we started designing generators and all sorts of ways of stopping that happening again. And then we realized very quickly, this is a solved problem. People have redundant power everywhere. We should go and look at data centers. And at the same time, we're looking at this. We were talking to a large financial institution about using Lucy to run future computations. And they very quickly pointed out to us, which was quite a mystical challenge, that they couldn't use a quantum computer long-term because the data cannot leave their four walls. And what they actually meant by that wasn't their physical four walls. What they meant is the data had to remain within their data infrastructure, their IT infrastructure that their Chief Information Security Officers already signed off. The networks that exist, the security and the sovereignty that's important to them had to be compatible with the computer. And as we were looking at the data center and we're looking at all their generators and the way that they're going to keep their power redundant, the tour guide said to me, in that cage over there, that's a bank. In that cage over there, that's a credit card processing company. Here's a material science company. Very quickly, it became clear that these are the customers for quantum computers, and they're all in co-located data centers. If you have data, you're in a data center. If you have data, you can benefit from a quantum computer. So it became a very obvious thing to do. So Toshiko was designed to be installed into co-location data centers, and we'll come on to some of the challenges about that in a short while. So very quickly, we partnered with Equinix in Japan, and we installed Toshiko right here. We've got 5 Toshikos in the world, in Japan, in Europe, and in London. We established our office, and today it says coming soon, but actually I'm pleased to announce we've now integrated deeply into data centers with a direct QCaaS, accessing quantum computers over the very fabric of data centers without using the public internet. And we're launching that right now, which is fantastic. So that's where we are today, and I'd like to talk a little bit about my view, OQC's view, and one view that we think is really important when we look at building quantum computers and how the industry is going to evolve around that. The first path, the first track on here, fault tolerance, I think is probably the most obvious for a quantum computing company. We need fault-tolerant quantum computers, FTQC, we have to build them, and everybody's building them, so that's fine. Some of the challenges we see with building fault-tolerant quantum computers is it's going to take a long time. There's a lot of engineering challenges that we have to get through to build fault-tolerant quantum computers. But the real key to that is we have to be really careful at the base level of engineering that we don't make fault-tolerant quantum computers impossibly complicated. So a few years ago, people thought that maybe error correction was impossible. Now we know it's possible. And people started saying you need 1 million qubits to build one logical qubit. That quantum computer would cost billions of dollars to make. Therefore, no one will ever be able to use it. We need to make sure we control the hardware efficiency of our processors at a hardware level, and then add all the layers of correction, suppression, and mitigation to build fault-tolerant quantum computers. So we have that roadmap like everybody else, and we see that we're going to move towards it. There's no point at which we are fault-tolerant. We're just going to get more fault-tolerant over time, but we've got to make sure that the infrastructure is in place for that, and that we look at the cost of what we're building so that it's commercially accessible. This middle channel around access, I think this is the thing we care about most within OQC. We don't see a world where someone that has a scientific challenge today, so let's say we have someone that works at an energy company, they have a scientific challenge around catalyst design. They go to work, they use their computer, they solve their scientific challenges, and they go home. In 10 years' time, when we've got fault-tolerant quantum computers, that person is still going to go to work, they're going to sit in front of their application and solve their scientific challenges. They're not going to turn around and use a quantum computer and use a classical computer. We have to start integrating these workflows and allowing access for people to seamlessly use quantum computers. We believe that quantum computers have a great place in research centers, but they have a really good place in enterprise as well, as long as we enable access to quantum computers. We need to enable access today for quantum computers. We need to inspire the next generation of software developers to start building algorithms for quantum computers and them to build applications for end users. There's a statistic, I think, from Experian or someone that basically said there was less than 4% of our accessible market actually know how to program a quantum computer. Therefore, the industry is stunted. And we've seen a lot of talks these past few days about new and interesting ways of accessing it. So for OQC, one of the most important things we can do, and this is why we launched an 8-qubit machine and why we've launched a 32-qubit machine today, is to inspire people to be able to develop algorithms and applications. So when we have fault-tolerant machines, we have useful applications as well. Those two things have both got to happen. That's super, super important. And then the last thing here, which I think is one of the often overlooked scaling challenges of quantum computers, is data sovereignty. So all over the world, there are geopolitical boundaries, there's data security. We know we need more than one quantum computer in the world. We know that empirically. We have a project that we have to run on a quantum computer in the UK. It can't run on our quantum computer in Japan because of data sovereignty. So we need to look at our business and the way we build things and the way we scale things to enable a world where potentially in 10 years, when we have fault tolerance and we have people that can use quantum computers, that there might be 1,000 quantum computers around the world. And that might just be OQC building 1,000 quantum computers. That might be quantum computers in 10 countries. And in each of those 10 countries, in 10 different data centers. And in each of those data centers, 10 different quantum computers, fault-tolerant quantum computers. That enables us to really look at things like supply chain. And it's interesting, the last talk from NPR around amplifier designs and things like this really stretches our imagination of how do I build 1,000, 10,000 physical qubit machines in 10 years? It's impossible today. We need to look at supply chain and work with partners and work out how we can do that. And at OQC, we really stretch our thinking to make sure that we're able to meet that challenge and demand as we start hitting these other scaling challenges on there. We also need to make sure these are fully integrated with high-performance compute, CPU, GPU, QPU. This is made possible because our computers are already in co-located data centers. That's a really important fact. So sort of coming back to today, we're pleased to introduce Toshiko. These are some of the specifications of Toshiko. This is Toshiko Gen 1. Toshiko is a superconducting quantum computer based on platform technology that enables us to consistently upgrade and run these computers, and it's specifically designed to be integrated into co-location data centers. In fact, Toshiko in Japan is in the Equinix data center on the 5th floor. People thought this was a hard challenge to do, but we've engineered cryogenics and superconducting circuits to work stably for months, if not years at a time, without resetting in the environments that our chief information security officers at the end users require us to be. That's a really important fact. Some of these are indicative snapshots here. The really important thing about these, when we built Lucy and we measured the specifications. Toshiko, we wrote down these specifications and then we set about building the machine. That's a real big engineering discipline for something that started in academia and is now fully in engineering. And we've built 5 of these, all to this specification. That's huge. That's huge for a company like OQC. Just very quickly, a visual of some of the machines we have here. You can see the sort of environment we're going into. I think if you asked any quantum engineer where they would build a quantum computer, they'd probably put it in a cave, like deep, deep underground, where there are no cosmic rays, no Wi-Fi signals, no electrical cables. That's not a reality. We need to deal with these kind of harsh environments. You'll find that everything in a data center, if you've ever been into a real genuine co-located data center, that whole place is vibrating. There's all the nasty noise that we don't want for quantum computers in there. And part of our challenge was engineering out all of those bits of energy so we could operate a stable service. So again, Lucy, our 8-qubit machine, ran for over 2 years. Toshiko in Japan has been cold now for about 8 months. We've done some fantastic work with our cryogenics partner, Oxford Instruments, and has been live for 6 months. So we're confident that cryogenic platforms are fully deployable around the world in the right environments, and that's a huge leap forward for quantum computing. Our job now is to upgrade the internals and the process in these using our Coaxmon technology to build fault-tolerant quantum computing. So going back to access very briefly, we know we need lots of access to computers, and that's how we're going to inspire this industry. My previous career, before I was in quantum, I was a video games programmer. I was a video games programmer a very long time ago. And there wasn't a video game industry. In fact, the first game developer conference I ever went to was about half the size of this. Now it's 30,000 people, and that industry is bigger than movies and music combined. And it grew like that because I could program and access my computer. We have to do the same in quantum. We need to give access to quantum computers. So today you can access via OQC Cloud. We've created a very easy, straightforward API for you to have cloud access to any of our quantum computers in the world. You can select which node you want around the world based on your data sovereignty, and you can start sending tasks to that. Today, that might be quantum assembly language or QIR, but working with software partners, we can start sending bigger and better applications to the machine. Really crucially for the development of commercial quantum computing, we've just launched Direct QCaaS. What Direct QCaaS means is that you can connect directly to a quantum computer through the very fabric of a data center. So if you are an enterprise customer, you will already have some kind of data center portal that's signed off by your security officer. Within that portal now, and under Equinix, you can literally select a quantum computer to be on your private network. So it's the lowest number of hops. It does not touch the public internet. It's like it's on-premise, but it's the lowest latency and the highest security that you'll ever get within a private network for QCaaS. This is the future of using quantum computers. We can connect directly to the person who goes to work and solves molecular simulation for their energy company. The quantum computer is right next to their high-performance compute and their data already. That's a really important step for us, and it's a really big scaling challenge that we need to overcome. We also do deployments. We've done a number of deployments, and by deployment, what I mean is if someone really does want a computer on-prem, it's something we can do. We did a wonderful project with our friends at Fujitsu in northern Spain to combine a Toshiko QPU with their high-performance compute. And it was a specific requirement of a customer to do that. But we firmly believe that the future of quantum computing is direct, low latency, high security QCaaS models. So just finally, launching Direct QCaaS, I'm really pleased to announce that we've had our first customer and our friends use Direct QCaaS already. So I'd like to introduce Minato-san, who's the CEO of Blue Cat, to come and say a few words about that.
Thank you, Simon. 今回はですね、私たちも
So this time, thanks to OQC, within our data center, utilizing Equinix Fabric, we ensure secure data for our customers. We can provide latest research data through direct connection. We can actually utilize quantum computing. This is a very service that we are providing to our customers. In the era of future data center, I believe future data center will rely on quantum computing. We can secure your research data. We want to provide appropriate technologies to our customers.
Very much. So thank you very much for that. I think it's a good endorsement of the future of using quantum computers. We know that people need to connect securely and directly. You can deploy your software server racks into data centers to access it. There's a QR code here to learn more about OQC and Toshiko. We're also in the bags that were kindly sponsored by Carmen at New Quantum. There's a leaflet in there for some free shots on Toshiko. So have a look at that. Please do apply. If you don't know how to use a quantum computer, you probably don't. There's only 4% of people that do. Please talk to one of the software companies that are here. They'd be happy to help you use a quantum computer. And if they don't know how to help you, please look for other vendors and application tools that will help you use shots on Toshiko, learn how to use quantum computers today. They're coming around quite fast. So with that, thank you very much.